Hi, and welcome back to learning about direct variation. This is the second video in a two-part video series, so if you haven't watched the first video, you probably want to go back and do that first. In the last video, we already identified direct variation equations, and in this video, we're going to write and use direct variation equations, and we're also going to use direct variation models and look at some graphs. So the first thing I want us to look at is an equation that models pressure and depth in fresh water. So doing a little research, we can figure out that pressure measured in psi given a certain depth in feet, so we're going to have pressure be a function of depth in feet, is equal to 0.432 times the number of feet you are deep. So remember, P of F represents our pressure and F represents our depth in feet. So if we look at this equation, first you want to decide, is this direct variation? Well, if you remember our direct variation model, remember y equals mx, or you could say y equals kx, or y equals ax. These are all the same thing. So basically we're looking for a multiplier times x. And if you look at the equation we've got here, we've got y. So remember P of f, or function notation, this is just a fancy way to say y, or our dependent variable, equals some multiplier, a constant of variation, times our independent variable. So we've got it. We've got dependent variable equals our constant of variation times our independent variable. It fits this model very well. So this is direct variation. All right, now think back to what you know about direct variation. Direct variations always have to go through the point 0, 0. So if we look at the graph of this, it should go through the point 0, 0. So here's a graph of what we've got, and if you look at the graph, I put it in function notation here. We can't put p's and f's into our calculator, so remember you have to turn things into y's. In this graph, I can use f of x instead of y because f of x is a fancy way to say y. And I've got f of x equals 0.432 times x, which is my direct variation equation. And then here I've put in some information so that I can have a point that I can drag around. So if you look at the point that's moving around, what I'm doing here, A is the depth, okay? So A represents the depth in feet, and then the Y value that comes out over here is the pressure. So let's say I want to figure out what the pressure is at 100 feet. I can change this to 100, and we can figure out the pressure is 43.2. Let's say I want to figure out the depth when the pressure is 30 psi. So now I need to change the y value so it's at about 30. Let's see if I can get it there. It's pretty close, so it's right about there. So my depth should be about 70. So let's go back and do that analytically and see if our answers agree. So the first question we wanted to look at is, what is our pressure at 100 feet? So what we want to calculate is our pressure given that we're at 100 feet. So what's going to come out here is 0.432 times 100, which equals 43.2, and that would be PSI, or pounds per square inch, which agrees with what we got on our graph. Next question is a little bit backwards. The next question I want to know is, how deep am I if my pressure, or PSI, is 30? Okay, so this time what we need to do is we need to put in 30 for our pressure. So we're going to say our pressure at a given depth in feet equals 0.432 F, and we're going to replace this because it's our pressure with 30. So 30 equals 0.432, and now we'll be able to figure out what our feet is. So we have to just divide both sides by our multiplier. So let's go ahead and solve this equation. Divide by 0.432. And when you solve that, you should get F equals 69.44. And if you remember when we were looking at the graph, we were at approximately 70 feet. So this also agrees with what we got there. Okay, let's look at another example that has to do with buying tickets. Okay, so here's some information. We're going to buy tickets for a concert, and the first thing we want to check is, can we write an equation, or can we write a model for this situation? So we need to decide, first of all, is there an equation that goes with this? And if you look at the cost per ticket, That's what we kind of want to figure out here. What's the cost per ticket? Go ahead and see if you can figure that out. You want to calculate the cost per ticket. Do that with your group. Go ahead and press pause and then start up the video again. Okay, so let's see. If you look at what you've got here and you want to make sure your cost per ticket is the same no matter how many tickets you buy. So let's test this. 36 divided by 2, you get 18. 54 divided by 3 for the second situation, you get 18. And also 90 divided by 5, you get 18. So it looks like no matter what, the cost per ticket is $18. Alright, now the next thing we want to do is, can we write a direct variation model for this? Now remember, $18 is the cost per ticket. And whenever we've got a slope or a rate of change, that's our constant of variation. So this $18 per ticket, this is our slope, or we could also call it our K for our constant of variation. So our direct variation model is going to be y equals 18x. Also, we know this should go through the point 0, 0, so we have a y-intercept of 0, because if you buy 0 tickets, you should spend $0. So that point should be on your graph. So we've got y equals 18x. This is our model that tells us how much we're going to pay for tickets. If you want to write this in function notation, you could definitely write cost based on the number of tickets equals 18t. So this would be a way to write it using function form. The cost depends on the number of tickets. All right, so let's go ahead and look and see how we calculated the slope here. If you look at the slope, we took the cost divided by the number of tickets. And the cost, this was our y variable, and our number of tickets was our x variable. So for each one of these calculations down here, what we did was we did a y divided by an x. Same thing here. This was a y divided by an x, and this was also a y divided by an x. Alright, everybody should be familiar with the slope equation. We've done it before. And when we're getting our constant of variation, or our slope in a direct variation model, y equals mx, remember one of your points is always 0, 0. So you have 2 points. You have 0, 0, and you have another point that is x, comma, y. So if we label our points x sub 1, y sub 1, x sub 2, y sub 2, and we plug this information back into our slope equation, our slope for our direct variation is going to end up being y minus 0 divided by x minus 0, or just y divided by x, like we talked about before. Also, if you look at what we've got right here, if we want to figure out what the slope is, if you want to get the slope all by itself, you go ahead and you undo this multiplication here. So you're going to divide both sides by x, divide by x, and what you get is the same thing. You get your slope equals y divided by x. So remember, whenever you have direct variation, you can quickly calculate your slope if you're given just one point. You can just do the y value divided by the x value. All right, you know a lot about direct variation now. Keep watching. Good luck on your homework.